I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me for this video looking here at a plane area calculation for a polar curve. Before we look at our question, let's look at a very basic fact. If you're looking here at a polar axis, here's your origin, here's your x-axis. As you can see, I project a certain vector at a certain angle. A certain point P develops. This point P will have two values in terms of x and y. One will be a certain variable, we'll call that a rho, and the other one will be an angle theta. That is a Greek alphabet for rho, and it looks something like a slant P. This representation is slightly historic. It is equivalent to the other more common representation, exactly everything the same. Polar axis, origin, x-axis, angle, a certain point P, you have a r and a theta. This r here represents a radius, and again you have the angle. Your rho here is equivalent to your radius. The distance or the dimension from the origin to that point, it'll be your rho, but it will also be r radius. You are looking here at polar curves. When you're looking at polar curves, you can say this is equal to a certain function with regards to an angle theta. But you can also say it's equivalent to this. The radius is equal to a function with regards to that same angle theta. These are two different representations. It doesn't matter what you use, they're both the same. Here I'm using this one because I'm kind of used to it. In all instances, the rho is always equal to your radius, and you know that it's equal to a certain function with regards to the angle theta. The plane area, how do you determine the plane area for polar curve? There's a certain formula. The plane area is equal to 1 over 2 integral lower limit, upper limit. You have that certain function with regards to the theta, and you will square this and d theta. When you bring this in terms of both of the nomenclatures I've shown you, you can say A is equal to your plane area 1 over 2, a lower limit theta 1, upper limit theta 2. You can have your rho square d theta. You can have everything the same, and you can say A is equal to your plane area 1 over 2, lower limit theta 1, upper limit theta 2, r square d theta. Both of these are equivalent. I'm looking here at this in this video. What exactly is our question? And we'll look at it on the computer in terms of the software. We have to find the area of this particular rose curve, which will be a cosine 3 theta. But we have to specify limits, because without specifying the limits, it's impossible to determine the area. We have a rho is equal to a cosine 3 theta. It's a rose curve, and it has 3 leaves. This here is also same as r is equal to a cosine 3 theta. This value a here is just a constant. It will represent how far out that rose leaf extends. It's kind of a, on your x-axis, if you're looking here of a polar axis, you're looking here on along the 1 dimension. If a was equal to 1, your leaf will come out up to here. A is equal to 1. If a was equal to like 5, your leaf will come out here like this to this value here, which will be a equals 5, and you can see it. It depends on how long your leaf will be based on that value of a. Here we're keeping a general. We're not specifying the exact value. We'll treat it as a constant. Now this right here is our representation. Let's switch over to the computer and see exactly what it means and what it displays. Now we're looking over here at this online software graphing tool. I'll give the credit in the video. You can look at the information tag. Anyhow, this right here is our function. The r, or the rho, with respect to theta is equal to, I've put here a value, let's put 1 by keeping it generic. We have a cosine 3 theta where a is equal to 1. Here obviously with this tool you have to specify the value of a. Our domain is 0 to 2 pi. When you do 0 to 2 pi, the domain, you get the complete 3 leaf rows develop as you can see it. When I zoom in, you're seeing it, and it looks just like this. This right here is an a value of 1. If I were to change the a value to, let's say, 3, your leaves will become longer, and now I have to zoom out to see it in its entirety. You're looking here, it's coming here to a value of a equals 3. So that's the meaning behind a. A will extend your leaf out to a specific value based on that value of a. We have to pay particular attention to this domain 0 to 2 pi. When we're doing our integral, we're not going to do 0 to 2 pi because it'll be complicated to do a area determination of 3 specific leaves. What you want to do is focus on only part of a leaf. If I were to change this domain from 0 to pi over 6, look what happens, pi over 6, and I get rid of this a value and I keep it a equals 1. So we just bring the leaf back in. Now we can just zoom in. This is what we're looking here. We're looking here at half of a single leaf, but in the first quadrant. We can determine the area of this half leaf multiplied by 6, because half times 6 will give you your 3 total leaves. So this is our game plan. We're going to use here a domain, lower limit 0, theta equals 0, upper limit theta equals pi over 6. We'll determine the plane area of a single half leaf. We'll multiply it by 6 because it'll give us our remaining representation to include the 3 leaves, meaning the 6 halves, and we'll have our plane area. Now let's switch back to our board. Now we know what to do. We have area is equal to half. I've already given you our lower limit 0, upper limit pi over 6, because what we're doing is looking here at only this half of a leaf. Here's my a comma 0, we're not specifying it. We're doing this. We'll multiply it by 6 because then we'll get everything else. As you can see, it will develop and it'll look like this. You'll have 6 halves to give you 3 total leaves. That's what we have. And then when we complete the picture, it looks something like this. As you can see, that's what it is. That's our game plan. We have over here a row or a radius. It's a cosine 3 theta, but you have to square it. It'll be a square cosine square 3 theta d theta. This here represents our integral. When you do 0 to pi or 6, lower limit to pi or 6, this right here is your 0 radians, and then this right here will be the angle, next angle, pi or 6. You're focusing on a single half multiplied by 6 to complete the picture, and we determine our area. So now that we have this, what we do is bring in our integral. I have a 6 coming in, I have a 6a, so I have to multiply 6 here, because as you know why that's the case. 6 times 1 over 2, we have 3. We have the a square, it will come out as a constant, 3a square. I have a 0 pi over 6 cosine square 3 theta d theta. I'm thinking here about a half angle or a power reducing identity. You know it. Cosine square theta is equal to 1 plus cosine 2 theta over 2. This 1 over 2 can push out. When I push it out, I bring it out. I'm left only with this 1 plus cosine 2 theta, which now I have to bring this into this form. I'm looking here at 2 and a theta, but here I'm already looking at 3 theta. I have a 2 times theta, but my original theta is a 3 theta, so I have a 6 theta come about. When you bring the half angle formula or the power reducing identity, you have these items come about as I'm showing you. What we will have over here is this. We have our 3a square over 2. I have a 0 pi over 6. I have that 1 plus cosine 6 theta d theta, and this right here is our integral. In case there was any confusion, it's going to be re-spelled out for you. Cosine squared theta is always equal to 1 plus cosine 2 theta over 2. The 1 over 2 is isolated and brought out. You have this. You have a 1 plus cosine 2 theta. My original theta is a 3 theta. 2 theta times that 3 theta is 6 theta, and everything plays out properly and it looks good. This is what we have. We can separate everything into 2 separate integrals across the positive sign. When I do it, I'll have here a 3a square over 2. I have my 0 to pi over 6 d theta plus 3a square over 2. Then I'll have a 0 pi over 6 cosine 6 theta d theta, and that's what we have. What we'll do is focus on the first integral. When we focus on that, it's easy. The antiderivative is a theta. I have here 3a square over 2 theta as my antiderivative coming from right here. Pi over 6 and a 0. Upper limit, lower limit, difference of the two. 0 is meaningless. You will have 3a square over 2 times pi over 6. When you compute this, you'll have a pi a square over 4. 3 divided by 12, 1 over 4, and this is it. So I'm looking here at a pi a square over 4 come about from the first, and I'm putting it right over here. Pi a square over 4 is coming from the first part of the integral. Now let's look at the second part. The second part is not hard. You have to do u substitution. For the second integral, we're using u substitution. If u is equal to 6 theta, then I know du is equal to 6d theta. And then d theta is equal to du over 6. I'll have new limits. u1, 6 times 0, 0. u2, second limit is a 6 times pi over 6, which is a pi. What's the antiderivative of a cosine u? After you've done your u substitution, you have a cosine u. What's the antiderivative? It's a sine u. When you're looking at it from my pi and a 0, I'm ignoring the fact that I have a 3a square over 2. I'm ignoring the fact that I have a d over 6. Why? Because when I do this, I'm going to zero out. This is a 0. This 0 will nullify all of this entire integral, meaning My entire area for that rows is coming only from the first part of the integral, and the area has already been determined, pi a square over 4. So the end result of this entire calculation is we have our area for the rows, the 3 leaf rows, and it's pi a square over 4, bringing into fact that we have the 6 already in play. My area for that rows, a cosine 3 theta, using the limits 0 to pi over 6, is going to be pi a square over 4 units squared, and it will be correct. This answer right here is correct. And that right there will be the end of this video. Thank you for watching.